So I know I said I would start today picking up where I left off with capacitors, but just so we don't just keep falling behind, I'm instead going to upload like a video solution to that capacitor problem that I put up yesterday, and with that I'll kind of just go through everything there is to go through with capacitors. So that will take the place of that. You will not see capacitors again until the final, or like reviewing for the final, but it'll be there for whether you want to review it now or then or both. So we're going to pivot away from steady state flow, exponential change, circuits altogether, and move to more typical physics that you see usually when you first start out in a college physics course, which is with like momentum and forces and all that good stuff. But first we need to learn how to talk about them, so develop a language for it. So scalar quantities are what we've been talking about so far in this course. They have a magnitude but no direction. So things like mass, energy, temperature, right? Like something has 3 kilograms, or something weighs 3 kilograms. No more information is necessary. A direction makes no sense for that. Same thing with temperature. 79 degrees in here, that's plenty of information. Maybe a unit we add onto a scalar quantity, but no direction. There's also scalars like speed, how fast something's moving. That also doesn't need a direction, right? I tell you something's moving at 10 meters per second. That tells you how fast it's moving. You could calculate kinetic energy. Great. But speed also could have a direction attached to it, which makes it a vector quantity. Well, not speed. The speed plus direction, velocity, is a vector quantity. So they have a magnitude, just like before, but also a direction. And so things like position. I tell you an object is 3 meters away from you. That is not the whole story, because you could be 3 meters in front, 3 meters behind, 3 meters this way. So you need more information. Forces, momentum, velocity, all of these things are different vector quantities where they have both an amount and a direction. So velocity here is that when you have speed and a direction. We've only been talking about speed because we haven't been concerned with the direction. We know it's confined to flow in a circuit, and we only care that it's going like in the direction of current or whatever. Now we'll have a direction attached to it, which is why sometimes I said velocity in previous lectures but then corrected myself because I did not assign a direction, and so it was a speed. So how do we represent vectors? Well, graphically is a great way, and the arrow is an amazing tool to do so, and that's how we're going to do it. So f with a little arrow over it, that's how we denote a vector quantity. So you just write that variable with a little arrow over the top. But arrows are how we graphically represent vectors. Why? Because they have a magnitude built in. It's just the length. And they have a direction built in. It's the direction. So it's an object that perfectly contains all of the information we need to describe a vector. And so we'll make great use of them. There's a couple examples. Here's two position vectors, x1 and x2. So x1 is representing a position that's a little bit north of the origin. x2 is representing a position that's to the east or to the right of the origin, a little bit further away than x1, but in a different direction. And all of that I found just from seeing the length and orientation of these two arrows. So that was for position. Another example is speed. Velocity. These two velocity vectors, they're both moving in the same direction. So both of these represent objects that are moving to the right with some speed. And v1 is larger than v2, so this object is moving faster than this object. So it's just a very easy graphical way to describe these. But the utility of these arrows goes even further, because we can actually do arithmetic graphically with vectors as well. So let's say I have these two vectors, F1 and F2. They're forces. We haven't defined forces yet, but it's just a type of vector. So just think of it as a magnitude and a direction. And to add them graphically, we just add them tip to tail. So we stack them. So really, you think about it as just like following from the beginning of one, like through the arrows. So you just place them in a chain, and then you identify your start and finish, start and end, and draw a new arrow that goes from your start to your finish point. So algebraically, adding vector 1 vector f1 plus vector f2 gives me this new vector fnet. And that applies for as many vectors as I have. So if I have an f3, I just add that onto the end of f2, and my new fnet is whatever my new endpoint is. So let's do a practice one with that. Here's two vectors, f1 and f2. Based on that, what is fnet? All right, I'll stop us there. So we know that to add vectors graphically, we want to place them tip to tail. So the answer is C, and we'll see that if we take f1 and add it to f2, we just put them one after another, and we get fnet, which is this vector pointing up and to the right. And it's important that I go from the start to the finish. So you want to follow the direction of the arrows. And that's how we know it was the one pointing up and to the right, not down and to the left. Another important thing you might notice here is that I added f1 to f2, even though here I wrote f1 plus f2. And that's because the order does not matter. Just like with normal addition, right? 2 plus 3 is 3 plus 2. It doesn't matter. Same thing with vectors. Even if you have the long chain of them, you're adding 10 vectors together, all the different permutations, adding them, whatever, you're going to get the same fnet when you add them together. All right? And I won't actually have you answer this question, but same question, just rephrased. I've changed the f's, not all of them, I forgot a couple, to p's. So now they're momenta. And it's the same exact question. So I was just trying to emphasize here that this rules of vector addition, the way vectors work, don't change depending on whether this is a position vector or a force vector or a momentum vector. They still add the same, and you obey the same rules. But just like in normal scalar quantities we've been working with, I need to have the same units, right? I can't add meters to kilograms, so I can't add a momentum vector to a force vector. I need to work appropriately with them. All right, we talked about addition. For subtraction, some people, and maybe your TAs will go over this, like to add like some other rule with like adding the tips and the tail. I don't like it to think of it that way. I like to just always do tip to tail, as in just like take one arrow and put it on the end of the other arrow in the direction that they want to go. And so to do that, let's just turn the subtraction into addition. And how do we do that? Well, 2 minus 3 is the same as 2 plus negative 3, right? So f1 minus f2 is the same as f1 plus negative f2. And to get the negative of a vector, we just flip it around. So put the arrowhead on the other side. And so now we can add them the way we normally do, tip to tail, and draw our result, our f difference. I've labeled it here. But I just took f2, flipped it around, and popped it on the end. And so my difference vector looks like that. In some cases, yeah, vector addition can be a little, not counterintuitive, but it's less easily seen right away because when you subtract things in different directions and stuff, it's not clear why that subtraction. So that's why I think vector subtraction is better just thought of as addition with one of them flipped around. Okay, questions on graphically combining vectors? Yeah. Exactly, yeah. All right. So our representation of vectors graphically is great, and it helps us move stuff around. But we, of course, want to solve problems and do physics with these, so it'll be important for us to represent them algebraically as well. And to do that, we just need the same things, a magnitude and a direction. So now our magnitude is, well, a number, an amount, and our direction is, well, an explicit direction. So here F1 might be a force with a magnitude of 4 newtons, and the direction is 30 degrees north of east. Then this one has a different magnitude and a different direction. A key thing to notice is that you can't just specify an angle. You need an angle as well as an axis of reference, or like, what is this an angle from, right? If I just tell all of you to run in a line that's 30 degrees, like that doesn't tell you anything. It needs to be 30 degrees what? 30 degrees from to the right of in front of you, 30 degrees south of east, it doesn't matter. There's a lot of ways you could phrase it, right? I could, instead of saying north of east, so here's my like cardinal directions, I could go north of east, or I could just say like counterclockwise from the positive x-axis. When you do problems, you'll run into a bunch of different ways of phrasing it, and there's no one correct way, but what you need, in addition to the angle, is where that angle is from. Okay, so this is great. This makes it very easy to to communicate about vectors, right? Magnitude and direction. What more is there to ask? But it doesn't give us a clear way to add them together, right? So again, good way to communicate, not a good way to add. If I told you to add these two vectors together algebraically, we know graphically we just add them tip to tail, but how do I add something that's pointing this way? Like, how do I add 30 degrees to 60 degrees? Do I just like subtract them, or is there some formula? Like, no. We're going to need a different way of expressing them algebraically, and that way is by using components. So here's this vector F1. I haven't done anything to it. I've just put in the background a coordinate axes. So now I've defined the y direction is up and down, and the x direction is side to side. And what that allows me to do is identify the x and the y components of f. So now I have this vector F1, and it has some extent in the x direction. So how far does it go in the x direction? That's F1x. And then I have some extent in the y direction, F1y. And we can express this vector. You'll see it just like in parentheses. It's like a coordinate of where it ends is basically what this is. But you have your x, comma, your y component. So this is a much better way, we'll see why soon, of expressing vectors graphically, well, at least for solving problems. The other way is still great for communicating, just a magnitude and a direction. But giving us the two components is a much better way to solve problems. Another way you can think about this component setup is that each component you can think of as its own vector that's only in one direction that contributes to our vector. So if I make fx the extent of this vector in the x component, just make it its own vector, make fy the extent of this vector in the y direction, we know, it's already done for us. We know how vector addition works, right? You add them tip to tail, which fx and fy are already arranged like that, and they add up to f1. So components are a very powerful way of dealing with these vectors, and it reduces them into pieces that are only in the x direction and only in the y direction. And that's why they're useful, because I know how to add an x, like a value in the x direction to a value in the x direction, right? That's just addition in one dimension. Same thing for y, that's addition or subtraction or whatever in one dimension, and so that separates the problem into pieces that I can deal with algebraically. So let's kind of put that all together, our graphical, and see how this algebraic approach is working. So now I have those same two vectors as before, f1 and f2, that I wanted to add together. And now I've identified both of their components. f1 has a positive x component and a positive y component. f2 has a negative x component and a positive y component. So if I want to add them, then I'm going to do it component by component. So f1x plus f2x is one equation, and f1y plus f2y is another equation. And that combines to give us fnet. So everything from that is just put on one slide here. Fnet is its own vector with an fnet x and an fnet y component. And those components come from the sum of the components of the individual vectors that make it up. And they're completely independent. So that's really the value here as well, that the x direction and the y direction are essentially two separate problems, right? So if we're doing these problems, we don't want to have to deal with all this crazy math with two variables, two directions going on. It's much easier to just take the problem, break it down into horizontal and vertical, solve those, and then put it back together. Another just visualization of this, we can just think of it as adding vectors the way we normally add. F1 plus F2 equals Fnet, and we get the components added together. Okay, so going back, combining this with the graphical approach. We add them tip to tail, right? So let's do that here. I've added F2 onto the tip of F1, and we draw Fnet. So graphically, we see that this works out. And let's see what's going on with the components. In the y direction, I have F1y plus F2y, the extent of F2 in the y direction, and that gives me Fnet, the extent of Fnet in the y direction. So you can see how the graphical approach and the algebraic approach are giving us the same result. They're inherently like the same thing, just using a different way to express it. In the x direction, we have the extent of F1 in the x direction, F1x, and then we're adding to it a negative x component for F2. Right? F2 has this negative x, so Fnet x is less than F1x. And that's how we get the final x component of Fnet from adding these two. But here you can see like the just coalescing between the graphical approach and the algebraic approach, component by component. They are really the same thing. The algebraic approach is just describing exactly what's going on here. Okay, let's do a practice question. Here's two vectors with their components. What are the components of Fnet? And as an extra bit, you can draw it too. What does Fnet look like? I'll give you 15 more seconds or so. All right, so to add these two vectors, we just do it component by component. So Fnet x is going to be F1x plus F2x, so negative 1 plus 3 newtons. So we get 2 newtons. And for y, we get negative 2 plus 0. So we get negative 2. And so Fnet is 2, negative 2. And so we know what vector that looks like. 2 is positive in the x, and then negative 2 is negative in the y. So our vector should be going right to the right and down. And if we draw it out here, add these two vectors tip to tail, we see that Fnet does indeed point to the right and down. Questions about this one? All right. So now we have these two compatible, but we have to see why. We have two different ways to talk about vectors, either the magnitude, the length, and the direction, and the components, and how do we go back and forth in between them. So they both still have their value. One's great for communication. One's better for doing problems. And if you haven't guessed already, the key to finding fx and fy from these two, the magnitude and the direction, or vice versa, is trig. So I'm not going to spend a lot of time going over it right now, sine, cosine, and tangent, and their inverses. If you're not comfortable with them, I would recommend just like looking up some YouTube videos. Like there's a lot of different ways people visualize it and go through it, but that and some practice should get you there. They're going to be a really important foundation, like learning how to use these, and the less time you have to spend using, like the less time it takes you to figure out whether or not to use sine or cosine or whatever, the more time you'll have to focus on the physics in the problem. So I'll talk through them as I do these, but But review some trig stuff and like that with that, the Pythagorean theorem that you'll see soon too. Just a little refresher, and that will be very helpful. Okay, so how do we find the components? Well, if I have the magnitude, the length, and the direction, the x component here, if this angle theta is the one I want to find, or the one I have, then fx is the adjacent side of this triangle. So adjacent meaning like it's touching that angle. And so we use cosine. Fx is going to be magnitude of f times cosine of theta. And fy is opposite, so like opposite theta. And so we use sine to find fy in this case. Great. And then if we want to go the other way around, let's say we have components and we want to find the magnitude and the direction. For the magnitude, we have the Pythagorean theorem, so it's the square root of the sum of the squares of the sides. And for theta, to find the angle, we have to do the inverse tangent. So to find this angle, we know fy is the opposite to it, and fx is adjacent. So it's going to be tan theta equals fy over fx, or theta equals inverse tangent of fy of fx. So rather than writing this exact thing down, like inverse tangent of the y component over the x component, or fx equals magnitude times cos theta and fy equals f sine theta, I would think it's better, well, it is better, to not memorize those and instead understand what the sine and the cosine are doing. Because what if I gave you this angle? Or what if you wanted to find this angle? In this case, fx is the opposite side, right? So now to find fx, I need to use sine. And to find fy, I need to use cosine. And with these, you have to make this comparison that this length here and this length here are the same. Question? Yeah, exactly. So either one's fine, but it's just you're giving more work for yourself here. Or like, what if I asked for this theta, then you could solve the problem for this angle here and then just find the complement of it, like 90 minus that. But I think it's much better to just know what the trig functions are doing and not to get tripped up. So y doesn't always mean sine. X doesn't always mean cosine. Sine means opposite. Cosine means adjacent. Yeah. Yep, so that for this angle, then yeah, east and north would be perfect. North is up, and east is clockwise. I could also say clockwise from the positive y-axis. All right, so let's do an example together. So I have this vector here, A, and the magnitude of the x component is 3, and the magnitude of the y component, even though it's negative, is 4. So I have my components, and I want to find the magnitude and the direction of A, and it should really be 3, negative 4. But hey, this is a learning opportunity, my typo here. We can define the axis however we want. I'm going to say the y-axis is positive pointing down. So that's fine, too. That's something that's important to note, is that there's nothing special about up and down, left and right, up being positive, right being positive. That's just a decision we make. And we'll usually make that decision because it's just one we're used to and it works well for us. But I can define any set of two perpendicular axes that I want. I could rotate this by 90 degrees, 45 degrees. I could flip it. It doesn't matter. As long as I have two perpendicular components, I can describe my vector that way. And we'll see that a bit later on. But for now, we'll usually just use y is up and down, x is side to side. So anyway, after that digression, here's my components of A, and I want to find the magnitude and the direction. For the magnitude, we just use the Pythagorean theorem, so the square root of 3 squared plus 4 squared. And then for this piece, it doesn't matter whether they're negative or positive, right? I'm just looking for a length. So whether this arrow is pointing down, or I flip it above and it's pointing up and to the right, or side to the left, it doesn't matter. We're just looking at the length. So the negatives, squared, so they don't come into play. And we get 5. So the magnitude of this vector A is 5. And for the direction, here's the solution. And now let's work backwards. I'm going to say that I found this angle using inverse tan of AY over AX. And so I found inverse tan of 4 over 3 is about 53 degrees. Which angle am I talking about here? Yeah? The angle of the x-axis, yes. So that angle, 53.1 degrees, describes this angle, this one that you could say it's south of east, or you could say it's clockwise from the positive x-axis, because I did inverse tangent of AY over AX, meaning AY is my opposite, and AX is my adjacent, which is true of this angle up here. However, I am missing something, and that is the actual descriptor. So I found the angle, and now I need to describe that if I want to say the magnitude in the direction of A, the magnitude is 5, and the direction is 53.1 degrees below the positive x-axis. Or again, I could also say south of east, and both of those are fine. Yep. Nope, and I'm about to do that. So another way I could do this is use this angle, and in which case I'd get 36.9 degrees, maybe east of south. And yes, I could do, if I really wanted to express this angle, or maybe the problem asked it, I could just find that one and do 90 minus that, which is true. 90 minus 53.1 gives us this. Or to get this angle theta, I could do inverse tan of opposite over adjacent, meaning AX over AY, which is flipped from before, and will give us 36.9. So all of these work. Yeah. The last one, you could, in those terms, would be south of east. Yeah. I prefer that terminology. Like, that's what we'll use in this course, because if you say like southeast, that doesn't, like, to me it's not clear whether that means like from here, like this whole quadrant is southeast, but I don't know. Yeah, so just whenever you list an angle, be specific about how you found, like know how you found it and know which angle you're describing. Questions here before we move on? All right, so now let's actually define what forces are. So we have a pretty good intuitive understanding of what they are. I think they're pushes and pulls, and they are a vector quantity. A force has a magnitude in newtons, and like how hard we're pushing, and a direction. So it is a vector. Motion of an object is determined by the net force on it, which means that like how an object is, change in motion of an object. So if I have a bunch of forces acting on an object, its motion is going to be determined by the net. So if all those forces cancel out, then the motion of the object is not going to change. And if F net equals, F net equals 0, motion of object doesn't change. And you can always have, that's like the simplest way to find the motion of an object is what I'm saying, is that if you have a bunch of things acting on it, just take all the forces and add them together first instead of, each one doesn't produce a different motion in the object. And that'll be clearer in a sec. Another additional thing, it's important to specify for forces that they're acting on something and by something, right? Or by B on A by B, it doesn't matter. But forces are applied on one thing to another. So like this is a force by me on the chair. And as a result, we'll learn the chair is creating a force that is on me as well. But when we have problems with multiple objects and multiple forces acting, it's important to be clear about which force is being produced by what and which force is being felt by what. So we'll use this terminology for most forces when it's not clear. Okay, so let's do a quick example. We have a picture hanging on the wall, and we know that it is motionless. It's just stuck there. And so that tells us that F net equals 0, right? If there's just an object and there's no motion at all, the motion isn't changing, and so whatever forces are acting on it must cancel out. And so what forces are acting on it? We know gravity, right? Gravity is pulling it straight down, but then there's also these two wires. And they produce forces that are not straight up, but in these opposite diagonal directions. So here are all the forces, and I'm labeling them F1, F2, and Fg, but we know that this one is the force by the string on the picture. Same with this one, it's force by another string on a picture. And Fg is the force by gravity on the picture. So these are all forces on the picture. The first step when we're doing force problems for now is going to be to use a free body diagram. And really what that just means is get rid of the picture. Just every object is a dot because we don't care about where on the object the force is acting. Right? I know that the wires are attached to the top and gravity acts on like the whole thing at the center of mass, but we just condense it to a point, and that makes it much easier to see that all of the forces acting on an object are coming from it. Okay? And now we also know how to combine these forces now to check to see if they equal 0. Right? We know graphically to add forces, you put them tip to tail. And in this case, if we do that, F1, F2, Fg, brings us right back to where we started. So my net force is indeed 0. They all cancel. But let's go a little deeper and see why that is using our component method. So back to our free body diagram where all the forces are coming from this point. They're all acting on the painting. And we can break them down into their components. Each of the string forces that's diagonal has a component that is up and a component that is horizontal. Right? So F1y and F2y are both up, but then F1x and F2x are in opposite directions. F1 is pointing up and left, F2 is pointing up and right. Fg just has a y component. Right? There's no side-to-side piece of gravity, so Fg is equal to just Fgy. And now we can compare these separately. Right? I said we can break these problems into the x and the y components to learn about what they need to equal to make this problem work out. So looking at just the x components, the x direction, I have F1x and F2x. And those have to be equal and opposite in order for F net x to equal 0. Right? If one string is pulling to the left and one string is pulling to the right, if the painting is not moving, then those forces have to be equal and opposite. And we can see that graphically, and we'll see it algebraically on the next slide. In the y direction, I have two small upward forces from the strings, F1x and F1y and F2y, and then gravity is this larger force that's pointing down, but they all have to cancel because the painting is not moving up or down. So the forces have to turn into F net y equals 0. So algebraically, this means in the x direction, F net x, which is equal to the sum of the x components, equals 0, and that just tells us that the x components are equal and opposite, like we just decided. And in the y direction, we have the sum of all three of these y components equals F net y, which also has to equal 0. And so we find that the sum of the two y components of the string forces are equal and opposite to the force of gravity. So this is just a simple example. We'll do a lot of these force balancing problems where we're told that the F net is 0 or the F net is something, and then so we need to find what has to be true about the components of the forces that make up F net. Yep. Well, the force of gravity, or as opposed, yes. I mean, any vector, like I said in the beginning, can be turned into a scalar, right? Like there's nothing stopping me from just saying like this is a 10 Newton force and saying nothing about the direction. So that would be a scalar piece. So I could tell you just the magnitude of the force of gravity. It just wouldn't be. Yeah. So the force of gravity is always toward Earth. So in all these, it's going to be straight down. Well, I mean, like this chair. Let's say like this chair is moving at a speed of 1 meter per second. That's a speed. We do I also know that this chair was moving to the left, so that would make it a vector. It just depends on what information we're given. So a force. To completely describe the force of gravity, yes, it is a vector, a force with a magnitude and a direction. But anytime we have a vector, you could just withhold that information, and it's still a valid force. Hopefully that'll become more clear when we do problems that ask you like just for the magnitude or something like that, or you have to find, we'll see examples of both. That's where we're going soon. Good question. Okay, so this one's kind of tricky, maybe trickier than you think. We got a cabinet sitting on a truck, and it's not moving, so it's completely stationary. What is the direction of the force by the truck on the cabinet? So there's no motion here, it's stationary. What is the direction of the force by the truck on the cabinet? And my hint, in addition to the fact that it is tricky, is that we know that F net has to equal 0 because it's stationary. Question? Oh. I'll give you 30 more seconds or so to discuss it. All right, I'm going to stop us there. So yeah, this one is tricky, and I think it's trickier because we're given too much, more information than is useful. If I just completely removed the truck and just had a circle, and I said this circle is stationary, and there is gravity, what direction must the force, what other force must be there to keep the ball stationary? Gravity's pulling down. And so if the gravity's pulling down, what force do we need to counteract that? Up, which would just be B. Once we add in this noise of the truck bed and the angle and everything, it makes us think like, oh, well, it's going to slide down, so I need to prevent it from sliding up. But at the end of the day, if nothing's moving, we have an object. We know gravity is pulling down on it, as it always does. Gravity's pointing straight down. And so if our net force is 0, the only thing we need to add to that to get to 0 is just equal and opposite to gravity. Yeah?
Is the only way to cancel out the magnitude of the force of gravity pushing down is to accelerate directly upward?
Yeah, or to provide a force, but yeah. Yeah, exactly. So gravity points directly down, so we need a force that's directly up. But that force can be made up of other forces. So this is the total force of the truck on the cabinet, yeah? If the truck was moving, depends on what direction. If the truck was reversing, no, then it would not be C. It would be none of these. Well, we can talk about that after. But let's go through this problem first. So the answer is B, and let's see why. The force of gravity points straight down, and as a result, to cancel it, like we said, the truck needs to apply an equal and opposite force. Where the other pieces come in, like us knowing that the truck bed is going to push like up and out, or the fact that friction is going to keep it from sliding, is that those things add up to give us the total force on the cabinet by the truck, right? So two things. One, there's two new forces that we're kind of learning about here. They're just forces, but they're kinds of forces. One is the normal force. That's the force that keeps objects from like passing through one another, essentially. So like if I just have my water bottle and I let go of it, it's going to fall because there's just the force of gravity and nothing canceling it out. But if I put my water bottle here and let go, it doesn't fall because the normal force of the table is directly canceling out the force of gravity. So that's what normal force is. It's like the things that keep things on top of other things. Friction keeps things from sliding along other things, as you probably know. And so friction acts along the surface. And those two can't, like friction can't act at all perpendicularly to a surface, and normal force can't act at all along that surface, which is why the normal force is perpendicular to the truck bed and the frictional force is parallel to it. A way to see that is like, this table will never, the friction from this table will never be able to just start pushing my water bottle to one side, right? The friction can only provide a force to counteract my push. And likewise, like friction will not pull an object into another or push it out. And the normal force won't just slide the object. I don't know. That might be not that helpful. But normal force acts perpendicular, friction acts parallel. And you can see here that if we apply those two, they actually add up to equal a vector that is perfectly vertical, right? If we just took F friction and put it on the end of F normal, it completes that triangle and gives us our F surface as our F net from the truck. So that's where all this other stuff is noise that's added in from the picture. But at the end of the day, we just want F net to equal 0. Questions here? Friction and normal force both act as much as they need to. So what I mean by that is there's some normal force on my water bottle right now that's keeping it from going in, and that's equal and opposite to the force of gravity on it. But now if I start pushing on this water bottle, clearly the force the water bottle is pushing down on the table is increasing. Now it's gravity plus the force of me pushing on it, but the normal force has increased to directly cancel it out. So as I push harder and let go, normal force is increasing and decreasing as much as it needs to. Same thing with friction. So with friction, let's say I'm pushing on my laptop, not hard enough to move it. I can push harder and softer, and the laptop still doesn't move. And what that means is the normal and the frictional force are growing and shrinking just enough to keep the object stationary. That's how they work. Until there's too much and then it starts to slide, but we won't talk about that yet. Okay, so now let's talk about momentum. So like when an object actually starts to move. So far we've had no motion, which means that there's no change in momentum. Then we'll talk about why that is, but F net equals 0. So momentum is what we use to describe the motion of objects. We already know about velocity, right? That's a way to describe motion, but it's not the whole story. Why? Well, if you were standing there and I toss you something that is moving at 3 meters per second toward you, you probably want to know more, which is the mass, right? If I toss you a golf ball versus a bowling ball, that's going to make a difference to you. You're going to feel that change in momentum, right? Despite the fact that they had the same velocity, there's clearly something more about the motion, and that comes from the mass. So momentum is this vector that's mass times the velocity. Mass is a scalar. It's just a number, like in kilograms, but velocity is a vector. So when we multiply a scalar times a vector, we basically just stretch it and give it new units. But let's say I had some velocity vector that's 3 meters per second, and I multiply it by a mass that's 2 kilograms, then I'm going to stretch it to 6 kilograms meters per second. But multiplying by a scalar doesn't change the direction. So velocity and momentum are in the same direction. Momentum takes into account mass. And from this little equation, you can see that the heavier an object is, so the larger the mass, the more momentum it'll have, and the faster it's moving, the more momentum. So with that original example, I toss two objects with the same velocity. The one with higher mass will have more momentum. And another way of looking at it, I have two objects with the same mass. If I throw both of them, one of them a lot faster than the other, that one will have a higher momentum. So both mass and velocity are important. change in momentum comes from, so delta P comes from a force applied over time. So forces cause changes in momentum. That's the relationship between the two. When we apply a force, we get a change, which is why on the previous slides, when F net, the net force was 0, we got no changes in momentum. Objects were stationary. But when we do apply a force, a net force that's non-zero on an object, we get a change in momentum, and objects change their motion. The delta T comes from, well, it's there because the units, for one, force and momentum have different units, but force times time gives you units of momentum. But also it does, I think it makes sense. If I apply some force to this chair, then it's going, like for half a second, it's going to get some momentum and move as a result. But if I apply that same force, I'm not pushing harder, but if I apply it for longer, I'm going to impart more momentum, right? So the more time that a force acts, the larger amount of momentum it will impart to an object. And we use impulse as a kind of way to describe it. So J net here, that's like the net impulse. Impulse is not a separate, like this new thing. Impulse has the same units as a change in momentum. It has units of force times delta T, but it's just the way we describe, like a force over a time delivers impulse. You can think of it like that. And impulse causes a change in momentum, but they're the same thing. So I apply some force for some amount of time. Right there, that gives me my change in momentum, but we call that impulse. So I don't know, I'm not a huge fan of like using this separate symbol J, but it's kind of just like an interloper, a mediator. And we could ask you for impulse, but it's really just saying what is the change in momentum, or how much impulse the force time delta T did that require. Okay. Yeah.
So the difference, I mean, just like to clarify, in these two equations, you're kind of having velocity contribute the time portion to momentum there, and then in this case, you have the actual change in time, but then multiplying it by the force to get, essentially that momentum is a number of like force by time.
Yes, exactly. And another thing that kind of made me think of too is to specify that these are instantaneous quantities. So when I say the momentum or the velocity of an object, that's the momentum at a given time. So these deltas are changes in time. So a delta P is the change in momentum from of an object before and after I applied this force. So before delta T and after delta P, or really throughout this delta T, how much did my momentum change from my initial to my final? So that's where this delta T comes in. Like during the delta T is where we get this delta P. Yeah.
So if you have a delta P, then for that equation about the mass and the velocity, it wouldn't be delta V?
It would, yeah. So if we just apply a delta to this top equation here, so like change in momentum, mass doesn't change, or usually doesn't change. So it is from change in velocity. So like when I apply a force over a time to this chair and change its momentum, there is some delta P. There's also a change in velocity, and that's so you can. If I multiply P by 3, I'm also going to multiply V by 3. So then what? Exactly, yeah. That change comes from the impulse that I delivered, and it's exactly equal to that impulse I delivered. So more about P, like when it comes to the changing of momentum, forces cause a change in momentum. You do not need a force if you have to keep constant momentum. So an object that's just floating along in space at 10 meters per second does not need a force to maintain that. Force only is needed to change it, whether it's to speed it up, to slow it down, or even to turn it. Right? If we turn something, that does change the direction, which is a part of the vector that momentum is. So that's a change in momentum, and it does need a force. But if you have truly constant momentum, constant motion, then the net force is 0. You know that. That's a mistake that you'll probably make, like we all make it. You see an object and it's moving, and so we think, like, what force is causing it to move? But that is not necessarily true if the motion is constant. In fact, it's not true. If the motion is constant, you know that F net is 0. So like in that truck case, someone said, what would happen if the truck was moving? Well, if the truck was moving at a constant velocity, nothing would be different, because that constant motion, that constant momentum in the x direction still means that the net force is 0. That cabinet in the truck, they're not speeding up, they're not slowing down, so there's no force needed to do that. Okay. Other things, we're going to talk about momentum of a system. So we'll have lots of objects in a system, well, not lots, 2 or 3 objects in a system that have some momentum, and they can interact. And so we'll want to talk about the total momentum of the whole system. And to do that, we just add them up. And we know how to add vectors now. We add them tip to tail or by component. And so our total momentum is just the sum of the momenta of the individual members. And then when we're talking about these systems, we'll have open and closed ones. So we've talked about if there is an F net, then there's a delta P, there's a change in momentum. And if there's no F net, then there's no change in momentum. The same is true about a system as a whole. If there is an F net, if there's no F net, we'll start with that. If there's no F net on the whole system, then the delta P total, so the sum of all the changes in momenta of each individual piece of that system, is 0. So like we'll see on the next slide, 2 objects that collide, if you consider them to be both part of your system, there is going to be a momentum exchange, right? When they collide, one of them is going to hit the other and is going to apply a force to it, and their momenta will change. So there's clearly forces and momenta stuff going on, but there's no outside force. The net force on the whole system is 0. And so that momentum can only be exchanged. The total amount is conserved. So that would make it a closed system. That F net is 0, so delta P total has to be 0. In other words, like all these exchanges of momentum are like equal and opposite. You could also have an open system, right? A group of objects with momenta, and there's some net force that you add into the system. You deliver some impulse to it, and so you can have a total change in momentum that's exactly equal to the net force times the amount of time it was delivered. So we'll see examples of both of those, but that's an important identification to make when you're doing any multiple body problem. Is this a closed or an open system? In other words, is there an F net? And if not, then there can be no total change in momentum. So let's look at a simple collision problem. I'll walk through this momentum chart in a sec, but the situation is we have 2 balls, ball 1 and ball 2. Ball 2 is more massive than ball 1, and initially, ball 1 is moving to the right toward ball 2, and ball 2 is stationary. Afterwards, so they collide, and afterwards, ball 1 is stationary, and ball 2 is now moving to the right with some unknown velocity or speed. So here, I mean, these are written without vectors. We can think of like the arrow part as telling us what our direction is. So like these are still velocities because we know both the magnitude and. Okay, so we have this before and after state where a ball hits another one, and now the other one takes off, and the first one stops. And we want to describe what's going on there between them as the system as a whole. And so to do this, we're going to use a momentum chart, which is really just a method of organizing equations. So this whole thing here is like a system of, I think, technically 6 equations. Most of them are trivial. It's not like you're going to get these like huge systems of equations to work out, but it's a very nice way to organize ourselves, accounting for all of our objects and accounting for the progress of time. So each row of our table here is for a different object and the total. So we have a row for ball 1, a row for ball 2, and a total, and then each column is a point in time. We have our initial, our delta, and then our final. So you can think of this as like kind of your during, but this is the change that occurs between initial and final. And then the definition of all these things kind of is why this reads as equations. When we go down a column, we're just saying that so this is the initial state. So at this moment in time, that's saying that the initial momentum of ball 1 plus the initial momentum of ball 2 gives us the total initial momentum. So reading down is just adding up all the momenta of each part of the system at any given point in time. And then when we read across a row, that's saying look at one specific object or look at the total as a whole and then just track the progress of time, meaning P initial plus delta P equals P final. Right? So this middle row is just saying the initial momentum of ball 2 plus whatever change in momentum of ball 2 there was gives me the final momentum of ball 2. So reading down or to the right across these gives you equations that are either summing up each piece or progressing through time. And so let's fill out, I mean, it's already filled out, but let's walk through how we can fill out this momentum chart based on the situation that we had described to us. So first thing that you should do, like I mentioned before, is identify, is my system open or closed? Are there any net forces acting? Not just exchanges, not the things trading momentum and stuff, but are there net forces acting on this system? And in this case is no. You will be told more explicitly if like there's no friction or like nor gravity something, but in this case I'm saying there isn't. Yeah, so in the initial state, ball 1 has a velocity, a constant velocity. Yeah, so we're like our initial starts after whatever caused it to move, caused it to do so. So we're starting where ball 1 has this constant velocity, which does not require any force, right? If ball 1 before it hits it is just moving at a constant velocity, has a constant momentum, no force is required to maintain that because it's not changing. Okay, so because there's no net force, our delta P total, which is not written out here, but we can see delta, this is our delta P column. This is where we sum up all the changes in momentum of objects, and this is my total row, has to equal 0. Right? If F net is 0 for a system, then this piece, this total delta P piece, is always going to be 0. So that's the first place to start. And if there was some net force, like let's say there was, I don't know, wind blowing on ball 2 or something like that, that net force times delta T would come in here, and that would tell us what our total change in momentum was. But since it's 0, total momentum is conserved. All right, now let's look at the initial state. In the initial state, we know ball 1 is moving to the right, and so we can put ball 1's momentum here, which is a momentum arrow moving to the right. And these charts are good because you can use them graphically and algebraically, and both at the same time. Right? I can write in the actual value here, or I can draw the arrow, and this chart works for both because we know how to add numbers, we know how to add vectors, and so they're great. Okay? So that's ball 1. Ball 2 initially is at rest, so its velocity is 0, and its momentum is 0. And then I can figure out what the total is, right? Because I can just add down this column that the total initial momentum is the sum of the two initial momenta. And so our total is just whatever momentum ball 1 has. So in other words, this is the momentum that the system is working with for the whole problem, right? Ball 1 has some momentum, and there's no external force acting to change what that momentum is. So since there's no delta P, that also must be the same momentum that we have ending with, right? Whatever momentum is in this system stays, and it's constant. Okay? Now let's take a look at our final column. We also know about that. We know after the collision that ball 1 has stopped. So now its final momentum is 0. And we know that ball 2 is now moving with some speed or velocity v final to the right. So now we can also put in ball 2's final momentum. We don't know what this v final is yet, but we've already figured something very important out to solving for it. Now we have this whole row, right? Our final momentum row saying that ball 1 is stopped. Ball 2 has this m2vf to the right. But we know what our total is. Our total final is just whatever our total initial was because there's no net force. It's conserved. So what we found, if we add this up, is 0 plus this has to equal this. In other words, m2vf equals m1v. Whatever momentum ball 1 had, it transfers all of it to ball 2. And so now ball 2 has that same initial momentum, or its final momentum. It has the same amount of momentum that ball 1 started with because all of it is transferred to ball 2. Does that mean they have to be going at the same speed? No, in fact, they can't be, right? So if these two momenta are equal, m2vf and m1v, we know m2 is bigger than m1, right? So that means v final has to be smaller than v, which I think makes sense, right? If you have a large object and a small one, if the small one hits the large one is going to move slower than the other one. So maybe think of it this way. You have your friend sitting still on a tricycle, and you throw a tennis ball at their back. And the tennis ball imparts all of that momentum into your friend, but the friend is not going to take off at the speed that the tennis ball was moving. They're going to, you probably won't even be able to observe it. It'll be so small. But there will be some small change in velocity. But since their mass is much bigger than the mass of the tennis ball, the momentum is still the same. Okay, so now we looked at the final. We found we've already really solved the problem. We found what v final is, but we still haven't finished filling out the momentum chart. We have this delta p column, which we can solve because we know the initials and we know the finals. So the deltas are as simple as subtraction, right? So we can think of it, I guess we can think of it two ways. You could ask yourself, what do I need to add to pi to get to 0, which is just the opposite of it, right? I just need something equal and opposite to add to get to 0. And so delta p for ball 1 is just minus whatever it started with. Another way to think of it, if you really wanted to write it out, I know the definition of delta p is p final minus p initial, right? So 0 minus this vector. And we know when we subtract vectors, it's just like adding the flipped around version, so 0 plus the opposite, or we get the same answer. But however you want to think of it, we know that pi plus delta p equals p final, or p final minus p initial equals delta p. Those equations are definitional. Okay, I don't know if that's a word. Ball 2, we have delta p that we also are looking for. This one I think is even easier. I start with 0 and I get to this, so the change must just be whatever this is, right? Whatever momentum it has at the end is whatever its change was. But we also could have approached getting delta p for ball 2 a different way, because now we had the top row and the bottom row, right? So we could instead say delta p1 plus delta p2 has to equal delta p total. And if delta p1 is this and my total is 0, then delta p2 must just be equal and opposite of delta p1. So what we found is essentially that what occurs here is a momentum exchange, right? There's no external force that's acting and changing either or both of their momenta. It's ball 1 has all of the momentum, gives all of it to ball 2, and that's the whole story here. So that's an example of how momentum charts can be a little more than you need. This is 6 equations, but we're only asked for one thing. I solved the equation, learned what v final would be before I actually finished filling out the momentum chart. And that's fine. I usually won't. Well, you'll get asked in DL and F&T to make a lot of these, and they're important, and you should. But on a quiz, I'll never ask you to make a momentum chart. Still highly recommend it. Most people succeed using them. They're a great tool, but I'm not trying to test your ability to use this tool. It's just your ability to know what all these equations mean and how final relates to initial and how systems work together. Is there a question somewhere over here? Okay. Cool. Okay, let's do a clicker question. So we have 2 carts. They both have equal mass and equal speed, but not equal velocity, because their speeds are oriented opposite each other. And they're moving toward each other, and they collide. So which one of these final states is not possible if there's no external force present? So no external force. right, I'm going to stop us there. So let's just go through these one by one. Well, I need to put up the answer, so the answer is B, but we'll decide why together. So if there's no external force, F net equals 0, that means the total change in momentum needs to be 0, which means that my final momentum and initial momentum, my totals, are equal. So whatever momentum I start with, I have to end with. What's P initial? Well, we have two equal and opposite momenta, right? The velocities are equal and opposite. They have the same mass. So the total momentum is 0, because those two arrows will just cancel each other out. mv plus negative mv is 0. So if my initial total momentum is 0, then my final total momentum also must be 0. So the way we're going to check whether these final states are possible is just making sure that they do have a total momentum of 0. So for A, we have two carts with, again, still the same mass, and they're moving now in opposite outward directions at a speed of v over 2. But the velocities are equal and opposite, which that adds to 0, right? We get negative mv over 2 plus mv over 2. We get 0. That's fine. So that just means they collided, and then they bounced off each other, and now they're moving a bit slower. That's fine. We'll skip B because we know it's right. C tells a very similar story as A. We have two equal and opposite momenta still. Now they're oriented out. In this case, they don't slow down. So that's also fine. They just hit, and they're moving away from each other at the same speed that they collided. D, now they collide and they stop. But that's also fine because m times 0 plus m times 0 is 0, and our total momentum is fine. That just means they collide and stick. Yep. Kind of. We'll talk about this more next lecture. It has to do with a loss of kinetic energy. So momentum is clearly conserved in A, C, and D, right? They have the same initial and final momenta and make sense, but the total kinetic energy is not staying the same. So we'll go there next, but different situations can result in different losses of kinetic energy. And in this case, losing 0 is like an ideal case. It never happens, but it just means that no kinetic energy was lost. Nothing was absorbed. In that case, it couldn't even make a sound. But okay, so A, C, and D are all valid final states, and we'll talk about the difference between those situations next time, I think. And that B, now we have two carts. They're moving in the same direction now. They're stuck together, and they're both moving to the left. So there clearly we have, it doesn't matter what that speed is, what that direction, we have some net momentum, which is not equal to 0, and so that is not possible. So B is the one that's not possible. Okay, that's all I have for today. There is a quiz next week, and it's pretty much on what I just covered. So static forces and vector addition and stuff like that, and vector and trigonometry, and collisions, but only in one dimension.